Hello everyone, myself Manish. I'm from University of Galway, Ireland, and this presentation will be in continuation with the previous presentation. So I'm presenting on characterization of wind turbine noise through a psychoacoustic approach. We are trying to look at the wind turbine noise using a psychoacoustic domain. So as we all know that wind turbine noise is associated, is a good source of renewable energy, but still there are many issues such as unwanted noise, and it is being associated with annoyance and the cognitive strain and other health issues as well. And the presentation will focus on the how the wind turbine noise will impact the level of annoyance. Now we conducted this study under Project Vincennes. So the whole aim of this project was to generate wind turbine noise annoyance map. And instead of using a conventional approach where we use LAEQ as an indicator, we try to go into the psychoacoustic domain of it. So the basic steps involved, and I'll be like majorly talking about the collection of data and how we conducted the listening experiment and how the noise stimuli were selected for the listening experiment. After that, how we developed the noise annoyance model and use the psychoacoustic indicators to develop the noise annoyance maps. So our site for the data collection was the Wexford Wind Farm. It is located on the on the eastern part of Ireland. We had around 14 measurement locations, which are indicated in green dots. And these locations were used to measure the sound pressure level data as well. It was a year-long process. At the same time, we recorded the wave files, which was used for the psychoacoustic analysis. So in total, we had around 167 noise recordings with a length of 10 minutes each. Talking about the availability of data, so this data covers the whole seasonal variability because it was a very long process, and at intermittent time, then we try to record the wave files. So this distribution shows like how we recorded the wave files at different hours of the day and in different months as well. So it covers the full spectrum. After this, this is a basic about the psychoacoustic approach. So psychoacoustic approach is like considered to be the more near to the human perception, and which is where we use loudness, sharpness, fluctuation strength, and roughness as a major parameter. So I'll be majorly focusing on these 4 parameters and how can we use this in noise annoyance modeling and perform the mapping of it as well. So just talking about the like how the data looks like, the maximum sound pressure level or like across all these 14 locations was around 56.2 dBA, and the minimum was 19.5. So it was quite below the like this is the general background noise level on the outskirts of Ireland. And when we are converting it into the loudness level, we can see the maximum loudness is going around 15.28 zones. So it's not very loud, but still that there are few patterns which are happening, and that is how people are reporting the level of annoyance. So just talking about the interrelation between, the correlation between different variables what we have used, most of the variables goes together. There's, for obvious reasons, LAQ and loudness will have the highest correlation coefficient, but which was followed by sharpness. And just an interesting point to note, there was a negative correlation between sharpness and roughness with minus 0.58. The whole point was that we wanted to utilize this data set for conducting the listening experiment, and there was a constraint that we cannot use the 10-minute recorded wave file for directly for the listening experiment because it will increase the experiment period also, and we might not receive good responses. So the length of stimuli what we used for the listening experiment, which was presented earlier also, was 90 second, and that is how we splitted the whole data set into 90 seconds fragments of smaller files. And and that is how we got around 1,000 audio clips. Again, there was a point like how to clusterize the whole data, and how to pick these audio stimuli from this thing. So I try to analyze the optimal number of clusters through this data set using the gap statistics algorithm, and which was set to 3. So 3 was the best number, like in what like we can cluster the whole group. Where we use the k-means algorithm, considering the 3 as the optimal number, the whole data was clustered. Again, it was like we had around 1,000 samples, and which sample to pick. So the closest 6 samples to the centroid of each cluster were picked, and they were calculated based on the Euclidean distance, and it was amounted to total 18 audio files. So total 18 audio files are used for the listening experiment. I'll just talk about like briefly about the cluster attributes. So we have 3 clusters now. So first cluster is talking about the higher level of loudness, sharpness, and fluctuation strength as well. Cluster 2 and 3 are like more in a moderate range of loudness, whereas cluster 3 also have very low level of sharpness and fluctuation strength. After that, we started with the listening experiment. Around 46 participants were involved in this. Genelec the 8330 speaker was used, and the sound levels were calibrated at the listener's position using the class 11 sound limiter. And during this experiment, they were involved in the the cognition task, and at the end, they reported the level of annoyance caused on the 5-point Likert scale. So this is the basic, in the most important psychoacoustic annoyance model by Zwicker, and we try to adopt it as a base model to compare the our next developed perceived annoyance model. So we calculated the perceived annoyance using we calculate the perceived noise for each stimuli, and grouped it across 3 clusters. So the image shows like how the annoyance is associated with across 3 clusters, and it is statistically like significantly different. At the same time, try to compare the calculated annoyance, which is the Zwicker psychoacoustic annoyance, and the perceived annoyance, and how it goes together. So there is a good correlation, and it is statistically significant. But I feel like we need to like improve a lot on this, because the R level is around 0.74, and it should go like more beyond. Talking about like which exact parameter was contributing majorly to the Zwicker's annoyance calculation and to the perceived annoyance. So for us, perceived annoyance is the calculated by us, and Zwicker's annoyance we directly adopted. So their loudness and sharpness played a significant role for Zwicker's annoyance, but in our model, only loudness was a significant parameter, followed by sharpness and fluctuation strength, but they were not statistically significant. So after that, we try to do the noise annoyance mapping using the psychoacoustic approach. So here we use the predictor lemma software and build the whole model in a virtual setup, and try to calculate the 1/3 octave data at each receiver. So the grid of 50 by 50 meter was considered, and the receiver was placed at each 50 meter, and the 1/3 octave data was extracted from the software, which that data was used to calculate the loudness and sharpness based on the specified the equations. If you noted the data in this, the fluctuation strength and roughness was not varying a lot. So we used the average level of roughness and fluctuation strength for this, and not calculated like how for each receiver. and try to calculate the noise annoyance for each receiver and mapped it. So this map is the loudness map. So and it shows like how it propagates through our site area, and it more or less the propagation of loudness is similar to the propagation of LAEQ. It drops significantly with the increase in distance. But when we are talking about the sharpness, there is a less reduction in sharpness with the distance, and the sharpness travels for a greater distance. So this the similar results are observed in other previous paper, but those were not in the context of the wind turbine noise. So finally, using the loudness data and the sharpness data and considering the mean value of roughness and fluctuation strength, we try to calculate the perceived noise annoyance map. And this is the noise annoyance map for the site we considered. The final conclusion, I can say that the perceived annoyance model developed by us highly correlates with this because psychoacoustic annoyance, and that it explains the good level of variance as well. But we need to consider other parameters, maybe other acoustical and non-acoustical parameter to model it in a more comprehensive manner. The fluctuation strength and sharpness showed good correlation with the annoyance level, but it failed the significant taste. And finally, the roughness and fluctuation strength need more investigation, because here I just considered the mean value, but we need to understand how it is being perceived at different distance as well. So the way forward, I can say, is since the wind turbine noise is more subjective, there's a need to consider large, a diverse group where people with different noise sensitivity, age group, and gender can be included and have a good comprehensive data set. At the same time, I think if we are getting some knowledge about the psychophysiological signals, like how the psychophysiological signals are getting changed because of the noise exposure, maybe we can talk about the EEG or the GSR signals. Those might reduce the subjectivity, and we will be able to try to understand like what exactly the wind turbine noise is like. What are the consequences on human health? And finally, there's a need to study the propagation of psychoacoustic indicators in a more comprehensive manner. There's very little research which is available to my knowledge, so I think that there's a need to work on it. So that's it for my side. I'm working at the Galway Sound Lab. Feel free to connect and have more questions. Thank you very much.